Standard Industrial. We created a series of tutorials to make sure that you have the information needed to get the most out of your Standard Industrial equipment. When you're done with these lessons, check out the other skill building videos on our YouTube channel. And thank you for choosing to make Standard Industrial part of your business.
In this lesson, we'll learn to develop a graphical program. A graphical program allows you to design a part by drawing out its shape instead of describing it with numerical values. Another benefit of graphical programs is they allow the computer to analyze the possibility of having part collisions or geometry problems with the tooling that you're using. To start from the editor screen, select the New Program button and then select New Graphic. You'll be prompted by the General Data screen. The General Data screen is collecting information about the material and the tooling you're working with. This is the exact same information that you populated in the General Data area of the editor screen when you were developing a numeric program. Begin by entering the width of your material in inches. So for this case, we'll say we're making an 8-inch wide bracket. Next, you'll want to enter the thickness of your material in thousandths. So for a piece of 10 gauge material, we'll enter 135 thousandths. Next, when we click on the resistance field, you'll notice that it's not accessible. Move to the material field, and you'll be presented with a list of materials to choose from. Each of these materials has a number following it in the description. That number represents the ultimate tensile strength of the material. So here we have a steel that has a 48,000 psi ultimate tensile strength. We can also choose from a different type of steel that has a 37,000 psi tensile strength. If you don't see a listing that matches your material exactly, choose a material that has the closest ultimate tensile strength to the material you're working with. Highlight the material, in this case steel 48, select OK, and you'll see that it's listed in the materials field. Also, you'll notice that the same ultimate tensile strength was populated automatically into the resistance field. Some older versions of the software do have a resistance field that is directly accessible and will not have a materials table. If you are operating one of those versions of the software, simply enter the tensile strength of the material that you're working with directly into the resistance field. Next is the station field. The station field is used on a press brake that has a multi-station configuration. In this example, we do not, and we'll cover multi-station configurations in a separate lesson. Next is the die field. Clicking on the die field will reveal the die list. You can select the die from the list that you wish to use by highlighting it and then clicking Insert. Next is the V-die field. The V-die field is only used if a four-way die is depicted in the control system. After years of experience, Standard Industrial feels that it reduces the potential for operator error to enter all dies as single-face dies in the control. This means that even four-way dies we enter as four separate single-face dies in the control. As a result, the V-die field is not used. Next is the die orientation field. The die orientation field allows you to affect the orientation of the die that was originally entered into the tooling database. Some dies are directional, and when they are originally entered into the tooling database, the operator chooses a standard orientation. If for some reason that die needs to be turned around and the orientation needs to be reversed, you tell the machine that the orientation has been reversed by placing a 1 in the die orientation field. If the die is being utilized in the orientation that it was originally entered in, then you simply leave a 0 in this field for standard orientation. In this case, we're not interested in reversing the die, or if you have a symmetrical die that does not have a directional orientation, you will want to leave it as it was originally entered with the 0 value. Next, clicking on the punch field will reveal the punch list. We select the punch we'd like to use by highlighting it and then select Insert. Next is the punch orientation. This works the exact same way. If you have, for instance, a gooseneck punch that was originally entered with the relief oriented towards the back gauge, you could come in and select 1 if you wanted to use the punch in an orientation that places the relief towards the operator. Otherwise, you'd want to leave it as a 0 in standard orientation. Next is the comment field. This field allows you to enter a comment to remind or cue the operator, perhaps if there's something special or something that needs to be remembered about this job. You can simply enter alphanumeric message to cue the operator. Next, let's look at the measures area. The measures setting tells the CNC control what perspective to use when defining the lengths and the angles of the part. The perspective is very important. When metal bends, the inside of the bend area compresses and the outside of the bend area stretches. And so these factors mean that producing the same bend length on the inside and the outside of the part actually require different back gauge positions. So your CNC control must understand the perspective that's been used to design your part. Now, all that can be put simply by just saying that if your part is designed by measuring it externally, you need to set your measure setting to the 0 setting, which is external measures. If your part has been designed by measuring on the inside of the part, then your measures need to be set to 2, which is internal measurements. Now you'll notice there's one other option here, and that is the 1 setting. The 1 setting is referred to as neutral fiber measures, but what this really means is when you set your measures to 1, the machine is going to go directly to that position without making compensation for stretching or from compression. So typically 0, most parts are designed with external measures, and so we do see that external measures is the most common setting. You do see some internal drawings, in which case we'd put a 2 here, but for this example we're going to go ahead and use external measures. Now that we have the general data section completely filled out, we've told the CNC control the width, the thickness, and the resistance of the materials we're using. It understands both the dies and the punches we're using, and it understands the perspective from which the part has been designed. Now we're going to click OK, and this is going to take us actually into the graphic drawing mode. In graphic drawing mode, you'll always start out with a line in the horizontal position. This is not always advantageous because your part drawing may be oriented vertically, in which case we need to reposition the starting line before we begin to draw our part. In order to rotate the line, you'll need to move to the arrow at the bottom left of the screen. Click on it to reveal other options, and in the other options you'll notice a button that says rotation. When you click the rotation button, the line will begin to rotate in a counterclockwise fashion. Continue to click the rotation button until the line reaches the orientation that you need to start in. Now, there is no way to counter rotate the line back in a clockwise direction. So for instance, if you wanted to start in a vertical direction and you accidentally overshot, it's important to rotate the line all the way back around to the vertical position. So you'll have to actually rotate the line in a 360-degree fashion back to the vertical position that you went past by accident originally. The reason that that is necessary is because you'll notice that there is one end of the line that stayed stationary. It was the pivot point, and the other end of the line that changed its location in the rotation. That end of the line is actually the active end of the line. And by active end, what we mean is that is the end of the line from which the next tangent will be drawn. So each line that you draw from your shape will come off of this end of the line. So if you overshot your vertical orientation, you couldn't just turn the line 180 degrees to where it appears to be vertical, because when you begin to draw, the line would extend downward off the active end of the tangent instead of going vertically as you intended. Depending on your version of the software, lines may be drawn either by entering information into the boxes on the right-hand side of the screen or by touching different points along the screen. We're going to cover both methodologies, but first we're going to cover the most basic methodology, which is by putting data in the boxes on the side of the screen. Now that our starting line has been rotated into position, the next piece of information we need to provide is the length of the line. The graphic here is highlighting our starting line, and this L always indicates the need for a length. So each time you see an L, you're being prompted for the length of the line. So here we'll tell the CNC that this line is going to be 2 inches long. You'll notice that the line increased in length, and now there is a circle at the end of the line. The circle is indicating the active end of the line, so you know that your next tangent will emanate from this point. Next, we're being prompted with an alpha. An alpha is always a prompt for direction. So in this case, we're trying to tell the control what angle the next line should be drawn from. There are two methods for entering direction. If you're choosing a standard direction, you can simply click on one of the arrows and it will move in a standard direction. So here we're moving at a 45-degree tangent. I'm going to click the arrow and you'll see that our line is drawn at a 45-degree tangent. Once again, we're now being prompted with the L for the length of the next line we've drawn. You'll also notice that this area scrolls vertically as we enter information. So the information about the preceding line has scrolled vertically off the screen and out of our view. If we needed to move back and actually correct an error, we could simply click on the back button and you'll see that the information we previously entered scrolls back into view, and the tangent that is now active turns red. So we could make a alteration at that point, but instead we're going to go back to our current line. It is now active because it has been highlighted red, and once again we're being prompted for the length of this line. This time we're going to say the line will be 3 inches long. And once again, we're now being prompted for direction. What is the angle of the next tangent line? This time, we're going to go vertically this time. And we're going to make the length of this current line 2 inches. Once again, we're being asked, well, what direction is the next line of the part? So we'll go back in and now look at numerical entry. We can choose the standard angles, but if we're entering a different angle, we can simply click on the numerical entry and plug in a specific value. At this point, it's important to understand that when you're entering numerical values, the positive or negative number controls which direction the line is drawn. If we enter a positive value, say of 90 degrees, the line will extend to the left. However, if we were to extend or want to extend the line to the right, then we would enter a value of negative 90 degrees, and that would extend the line to the right. And this behavior is true no matter what angle your line happens to be at. So in this case, our new line will give it a length of, say, 4 inches. We'll draw another diagonal line to it. And even though this line is in a diagonal orientation, if I enter a positive value for the next line, the line is going to extend to the left. Or if I were to enter a negative value, the line would extend to the right. So this behavior is consistent with drawing lines no matter what angle they may emanate from. With the shape of our part drawn, now we need to go to the graphic portion of the program and allow the computer to analyze the drawing to make sure that we don't have any possibilities of a part collision or any problems with the geometry based on the tooling that we have. Now originally when we rotated our line, you'll remember that we clicked on the arrow to reveal the other options. So we need to click on it again to go back to the buttons that were on the main screen. Down here, once we're finished with our drawing, we want to click on the Calculate button. This will bring us into the graphical screen and show us an image of a flattened workpiece on the tooling. At this point, we select Optimize, and optimizing is what tells the computer to determine whether the part can be bent. Because the computer did not return an error that says no solution, and instead has a bar that says solution found, we know that the piece we've drawn out can be bent properly with the tooling that we've selected. The solution bar allows the operator to view the different bending orders that can be used to generate the part. Take notice of the 4 buttons available on the solution bar. You see that the Continue button is highlighted, but also notice that the Simulate and the Confirm button are dark black text and they are available to select. In order to look at a particular bending order, we'll first select Simulate. When we select Simulate, the part will be flattened out, and now to look at the bending process, we'll move through each step by hitting the Continue button. Before we do, take notice of the black lines on the workpiece. Each of these represents a bend point in the bending sequence. Also, take a look at the black circle. This circle serves as a reference point to help you keep your bearing as the part rotates and flips during the bending sequence. So let's click on Continue to see the first bend. We've witnessed the first bend, and you'll also notice the black line disappeared once the bend was executed. We'll continue. We see now that our reference mark has moved to the other side because the piece had to be rotated. We will continue until each of the bends is executed. Reach the finished state of the part. We know this because there are no black lines left in the part. All our bends were executed, and we also see that the Continue button is highlighted, but the Simulate and Confirm buttons are not highlighted anymore. This tells us we're at the end of this particular bend. Once we've completed all the bends, we hit the Continue button one more time. This gives us the option to click the Confirm button. Clicking the Confirm button tells the CNC control that we want this solution, and then allows us to save the solution. If we want to continue and to look at other orders of operations that could be used to bend the part, instead of selecting Firm, we select Continue again. When we do, the final state of the next bend will be shown. So this is the position the part will be in after the last bend in the next order of operations. If we want to go through and see how each bend in the sequence occurs, just like we did on the first option, then we select Simulate again. The part will be flattened out again, and now we repeat the process. As we continue through the bends in these sequence, take a look at the right side of the screen here and notice that in the categories of upsetting and rotations that the numbers will change. This occurs as we go through the bend cycle because the machine is keeping up with how many times the part has to be upset, which means flipped over or rotated. So now we know we're at the end of this bend cycle again because all the black lines are gone from the part, also because the Simulate and the Confirm button are not present, and the Continue button is lit up still. We notice that as we complete this simulation, that to go through this sequence of bends to create the part requires 3 upsets and 1 rotation. So now we can finish the bend, and we know that because the Confirm button comes up, and this gives us the option to confirm this sequence and save it as the method we're going to use to create our part. Based on the part's geometry, there can be a large number of bend sequences available to make the part. You may not want to step through or simulate each bend in each sequence. If you want to move straight from one bend sequence to another sequence without simulating, just hit the Continue button. You'll see that it gives you the option to take a look at the next bend sequence, showing the part in its finished condition for that sequence. If we want to skip this sequence without simulating and look at the next one, simply hit Continue again. It's only when you hit the Simulate button that it will take you directly through each bend in the sequence. If you want to move from one major sequence to the next major sequence, simply hit Continue. As you've noticed, there are a large number of possibilities with this particular part. The natural question at this point is which bend sequence is the best solution. The control presents bend solutions that place the operator's hands farthest away from the machine first, and bend sequences that place the operator's hands closer to the machine last. This doesn't necessarily mean that one solution is better than the other. The actual operator needs to consider his own environmental conditions and choose the solution based on his own judgment. When you finally reach the last bend sequence and there are no more sequences available, the no solution error will appear. This is what indicates that you've run through the entire cycle of sequence and there are no other options available. When you reach this point, select OK. You'll have to go back and hit the Optimize feature again in order to come back up and be able to select a particular solution and save it. Before we do that, I want to point out one thing. If during this process or any other you had discovered that perhaps you made an error or needed to alter the part, the way to get back to the drawing feature is to hit Stop on the simulation and then to go to the Draft Workpiece button. This takes you back into the drawing mode and would allow you to alter your drawing and then bring it back in to calculate it and to optimize it. Now that we understand how to go back and make a revision if necessary, we're going to optimize again, and this time we're going to select Confirm, which tells the computer that this is the solution we've settled on, and now we're going to go to the old style computer icon, click on it, and we're going to give the program a name. Now we've named the program, we select OK, and the program has been saved. To check and see if the program's been saved, we can go to the icon that represents the program database, and in the program database we will see that I've made a key punch error and misspelled guard bracket. So let's look at how to correct that. Highlight the program, move to the menu button, and click on Rename. Here we have another opportunity to correct our program. Click on OK, and now we see the program is corrected and that it has been saved in the program database. You'll also see an image of the part as well as key part information. While most of this information is familiar to you, there's one new piece that we haven't discussed: the development number. The development number tells you how long the flat sheet of metal needs to be in order to end up the length that you've programmed based on all the stretching that will occur during the bending process. So for this part to end up exactly as you designed it, it needs to be 12.547 inches prior to beginning the bending process. This same development number is also visible during the graphic analyzing piece. So we're going to go back and I'll show you where that is. To go back, we'll enter the program. We'll go back into the calculation mode and where we would optimize the part, and you'll see that that number was contained in the upper right hand corner. There's a slight difference of 0.003 here. You'll notice it was 12.547 in the previous screen. That's just a rounding difference in the way the number is presented, but this development number tells you, once you have the program completed, how long the blank piece of material needs to be before you start bending the part. At this point, we've completely developed a part in graphic mode. We've saved the part to our program's database, and we're now ready to move into production mode and begin manufacturing our components.
I hope this tutorial has been beneficial, and if it has, we need to ask a favor of you. In order to keep this site visible and to continue to bring this material to you for free, we need you to become a subscriber. We promise if you do that we will not send annoying solicitations to you. The only time you'll receive notifications is when we post new material to the site. So please subscribe, and thank you again for choosing to make Standard Industrial part of your business.